Hello, everyone. Thank you for attending this session and giving me the opportunity to contribute the IEEE Sensors 2021. My name is MD Abdulla Al Mamun. I'm with the Department of Electrical and Computer System Engineering at Monash University, Australia. So my presentation title is Map-Aided Fusion of IMU PDR and RSSI Fingerprinting for Improved Indoor Positioning. So this is my presentation outline. At first, I will briefly discuss about target localization with the existing issues of the standalone methods. Then I will present the proposed system. Then I will show the experimental evaluation, and finally I will conclude the presentation. So target localization. Localization involves accurate positioning of a subject of interest. Localization can be performed both for the outdoors and indoors, though there are some conventional and widely accepted localization and tracking systems, especially for the outdoors like GPS. They are not practical to use for the indoors since the satellite signals are blocked by most of the construction materials. So the position accuracy in indoors is unsatisfactorily quite large. Different types of technologies with the various algorithms are implemented so far for indoor localization. The most common technologies include RF, optical, acoustic, and inertial technology. And the widely used localization methods include trilateration, triangulation, fingerprinting, and PDR, that is pedestrian data reckoning. Among them, the inertial measurement unit-based PDR and wireless local area network-based RSSI fingerprinting method have drawn a significant attention to the researchers due to their low cost and satisfactory results for the indoors compared to the other methods. Localization via pedestrian rate reckoning, PDR. PDR estimates current position with respect to the previous position by monitoring the person's movement via IMU sensor. Usually, an IMU consists of accelerometer, gyroscope, magnetometer, and barometer. And the typical PDR methods includes three main steps, that is step detection, step length estimation, and heading estimation. And to calculate the current position, these elementary equations are widely used in PDR. And localization via fingerprinting. Fingerprinting method is composed of two main phases. One is offline phase and another one is online phase. During the offline phase, a radio map is created by collecting geotagged fingerprint data, and position of a target is estimated in the online phase by comparing an unknown location with radio map as shown in this figure. Though the PDR and fingerprinting methods have several advantages compared to the other methods, still they have limitations. The use of PDR as a standalone technique for indoor localization is not effective, especially for long-run applications due to their accumulation of estimation errors. And for RSSI fingerprinting, the radio map is vulnerable to environmental changes, and the RSSI produces spatial ambiguity as well as temporal instability because of the effects of several factors induced by the complex nature of the indoors. Thus, even though the traditional RSSI fingerprinting-based localization can achieve better performance compared to the other standalone solutions, sometimes it is not enough to meet the requirement of some applications that demand higher precision. To solve those problems with the standalone methods, sensor fusion techniques are used that can define the target positions by fusing data acquired from multiple measurement sources. To achieve higher accuracy, researchers propose several advanced solutions that combine multiple standalone technologies using various kinds of sensor fusion techniques, including Kalman filter, particle filter, extended particle filter, etc. Though these techniques offer optimal performances, or when certain requirements are fulfilled, they impose a certain cost, and that is high, both in terms of complexity and computation, especially for applications with resource-limited wearable devices. So this study proposes a lightweight sensor fusion technique by leveraging the indoor map information that can fuse the IMU-based PDR with RSSI fingerprinting method to achieve high precision indoor localization. This is the architecture of the proposed system. As shown in the figure, the localization system is composed of three main parts, three main modules. One is the landmark assisted PDR. The next one is the sensor fusion based on map matching. And the final one is the RSSI fingerprinting. The PDR produces a quartz location that is used by the sensor fusion technique to integrate with the fingerprinting method for estimating fine-grained location. So for the landmark assisted PDR module, there are three steps. The initial step, step length heading estimation, landmark identification, and stem length and heading correction. So here, the initial step detection is performed by using the traditional peak detection and thresholding techniques, and the step length and heading are calculated by employing the typical double integration technique. And a landmark can be identified by detecting a user's motion modes and then applying specific rules by setting time threshold to each rule. To detect the various motion modes, study employed a decision tree-based motion mode classifier. So after detecting the landmarks, the PDR estimated initial step length and step directions are corrected by using the landmark graph. The next module is the map matching based sensor fusion module. This module performs three main tasks: position, searching, and exclusions. The main idea of the proposed fusion techniques is to exploit the IMU PDR estimated quartz location that selects a small portion from the radio map to which the RSSI fingerprint searching will be performed. To do this task, this module performs three main tasks, that is projection, searching, exclusion, using two map matching techniques and one searching method. The idea is illustrated in the slide. Suppose this is a portion of an indoor floor plan, and these dots are the reference points stored in the radio map. Suppose this blue dot is the PDR estimated quartz location. So here, the first map matching technique projects this PDR estimated quartz location to a point in the closest trajectory by using these equations. And then the k-dimensional tree, KD tree based searching algorithm is implemented to search the reference points that are residing in a region in the spatial domain. In this work, the region is a circle which is centered on the projected location with a radius equivalent to the maximum error produced by the PDR only method. After selecting the M reference points inside the circle, the proposed method excludes the points that are direct unreachable from the projected locations, like this. Here, the directly unreachable points marked by red color here, detected by checking the wall crossing using this map matching technique. And the last module is the fingerprinting based k-nearest neighbors based fingerprinting functionality. So here, the traditional k-nearest neighbor method is implemented to match a query fingerprint with the radio map. But in this research, instead of searching the whole database, only the reference points that are direct reachable within the selected circular region are considered for finding the k-nearest neighbor. Thus, the system can produce high accurate results with fast response time. This is the experimental area. A test path length of 190 meters is considered here. As this figure shown, the path start at the red circle, go along the green line, and then walk around the red line 3 times, and finally walk to this red square through a room along the blue line. 9 reference nodes are used as marked by the star sign in the map. This is the experimental setup. Data were collected using two sensor boards designed by our group, as shown in this figure, that includes IMU and XB module. The reference nodes are attached underneath the ceiling, and a user with a chest-mounted wearable device is considered as the target node. This figure presents the estimated route for different methods, including the PDR only method, the fingerprinting only method, the landmark assisted PDR method, and the proposed method. As can be seen, the PDR only method produces the worst path compared to the others due to the error accumulation, and the proposed systems are the best route compared to others without crossing any wall, as we can see by observing the pink line. The details of the location performance are presented in these figures. In this figure, the box plot demonstrates the proposed system considerably outperforms the other method with the mean and median error less than 1 meter. And the second figure demonstrates the superiority of the proposed fusion-based method in terms of localization errors accumulation distribution function. As presented in the figure, the proposed system can attain a localization performance with errors less than 1 meter for 70% of the cases, as we can observe from here. So in conclusion, this study proposed and implemented a map-aided sensor fusion system to fuse the landmark assisted PDR with RSSI fingerprinting method for high accuracy location estimation for the indoors. Future works include the evaluation of the system performance on a large scale environment for real-time application. Thank you very much for your attention.